Hello and welcome to the AI Research Roundup. I'm Alex, and today is May 7th, 2025. We are looking at a paper from Hugging Face's trending list, published about 8 days ago on April 29th, titled Skill Discovery for Software Scripting Automation via Offline Simulations with LLMs. This research paper tackles how tricky it can be to automate software using scripts. It proposes creating a library of pre-verified scripts using large language models in an offline simulation. This involves generating tasks and then refining scripts with feedback, even using a graph neural network, often called a GNN. A graph neural network is a type of AI model skilled at finding connections to explore how different software commands, known as APIs, or application programming interfaces, which are essentially sets of rules for software parts to talk to each other, can work together effectively. Building on that idea of creating a library, this figure really lays out the proposed offline simulation framework. It outlines two main stages. First, on the left, we have task creation. This involves a top-down approach, generating tasks from known software functionalities, and a bottom-up approach. This bottom-up part uses an application programming interface synergy graph, where the graph neural network helps identify promising combinations of software commands. Then, on the right, we see skill generation with trials. Here, large language models attempt to write scripts for these tasks, which are then tested, validated, and refined in a simulated environment. Successful scripts become part of the final skill set, that collection of reliable automation tools. Alright, and this table really quantifies the benefits of that curated skill set. It compares their proposed offline simulation framework, labeled ours, against a baseline method, which is just using a large language model to generate scripts on the fly. We see a big jump in success rate, from 28.7% for the baseline to 44.7%. Response time plummets from 4 seconds to just 0.1 seconds. And the runtime token cost, which measures how much computational resource is used by the large language model at runtime, drops from 666 to 0 because the work is done offline. So those impressive overall improvements are built on the two task creation strategies we discussed earlier, the top-down and bottom-up approaches. This table breaks down where the successful skills actually originated from in the test set. We see that the top-down strategy, which is guided by high-level software functionalities, contributed 35.1% of the successful skills. The bottom-up strategy, which explores application programming interface synergy, added another 9.8%. Together, these two methods achieve that 44.7% total success rate, demonstrating how both are important for creating a diverse and effective skill set. Now, delving into the mechanics behind these strategies. The first part of this visual, Table 5, compares methods for finding those synergistic application programming interfaces. Link prediction, using the graph neural network, scores a 37.3% hit at 5. This hit at 5 feet metric means it correctly identified a useful application programming interface partner in its top 5 suggestions over a third of the time, much better than semantic matching, a simpler meaning-based comparison method, which only hit 16.7%. Then, Table 6 shows the impact of iterative refinement. For the bottom-up tasks, success jumps from 23.1% on the first attempt to 46.6% after 3 trials, really underscoring the value of that trial and error process. Okay, so we have seen how these strategies find good application programming interface combinations and refine them. This next table then looks at the breadth of application programming interface coverage. It shows the number of unique application programming interfaces used by Illustrator's sample scripts compared to those built from the top-down and bottom-up simulation strategies. The sample scripts and the top-down approach both use around 48 to 49 application programming interfaces. However, the bottom-up strategy impressively utilizes 151 unique application programming interfaces, significantly expanding the range of software commands covered, which contributes to a more diverse skill set. Alright, so after building this diverse skill set, it is crucial to ensure the scripts within it are actually functional. This table shows a confusion matrix, a scorecard comparing judgments. Here, human evaluations of script success are compared against those from a large vision language model, or LVLM, an AI that understands visuals and text. When humans saw success, the large vision language model agreed 40 times, a true positive, When humans saw failure, it agreed 68 times, a true negative. It only missed 10 actual successes, called false negatives, and wrongly called 4 failures as successes, or false positives. This high accuracy shows the large vision language model is a reliable validator. So the high accuracy of the large vision language model as a validator is really key. In conclusion, this work demonstrates that an offline simulation framework, essentially a system that creates and tests software scripts in a controlled setting beforehand, is a very effective way to build a reliable skill set of automated tasks. This approach not only achieves higher success rates than generating code live, but also dramatically cuts down on response time and computational cost. It is a big step forward for making software automation more accessible and efficient. That is all for this AI Research Roundup. Thanks for tuning in.